Scientists study our world and everything in it. From the bottom of the ocean, the farthest reaches of space. But no matter how remote subject matter, discoveries are often made in settings like this, a science lab. Anyone who studies science is going to carry out scientific investigations. And whether you do it here or in the field, it's important to have certain skills. It's simply science. The best way to learn proper lab skills is by doing. Watch carefully. You'll need to practice. Exactly. Learn to plan and perform an experiment. Gather evidence, which may involve making observations, taking accurate measurements, or using lab apparatus. Record and analyze data. This may mean drawing diagrams and using graphs. With the right skills, you'll be able to carry out your own investigations.
We use scientific investigations to test and evaluate ideas. We start with a question. This leads to designing an experiment to answer that question.
How about, is light required for photosynthesis?
Sounds good.
We perform the experiment, record information, analyze it, and communicate our results.
If it's oxygen, this should reignite or glow brighter.
Finally, we determine whether the experiment answered the question.
And it does. So that tells us that oxygen gas was collected.
If so, was the answer what we had expected? Experiments may support or disprove a theory. Sometimes a theory changes as new information is brought to light. Let's look at an example of how a scientific investigation could be used to answer a question. The investigation begins with a problem statement. The problem statement could be, is light required to produce starch during photosynthesis? The problem statement leads to a prediction or a hypothesis.
If photosynthesis is a chemical reaction caused by light, we predict we'll find different substances in a leaf that's been exposed to light,
rather than one that's deprived of light.
You can plan your own experiment, or you can use someone else's design. Stephanie and Andy are using a geranium plant to show that light is required during photosynthesis.
This geranium has been in a dark cupboard for the past few days.
we're going to cover one of the leaves with a piece of aluminum foil. As you can see, we cut a small square in the foil to allow light to reach the top of the leaf.
Now, we'll place a geranium in a bright light for the next 24 hours.
During photosynthesis, plants produce glucose, and some of it is stored as starch. Stephanie and Andy will be testing for the presence of starch using iodine. They have a procedure for carrying out their experiment. This includes step-by-step instructions, what to do, what to expect, and what to record. It also indicates what safety measures should be taken and outlines the proper procedure for disposing of any hazardous chemicals. Before starting, Stephanie and Andy make sure they have the apparatus and all the materials they need to carry out their procedure.
The geranium has been exposed to bright light for 24 hours now. To prepare our leaf for the starch test, we put it in boiling water.
When the leaf becomes limp, we transfer it to another beaker half full of ethanol.
Stephanie and Andy follow their procedure step by step, making sure to record their observations.
We set the smaller beaker to this one to warm the ethanol.
Then we wait 5 minutes and see what happens.
Any kind of investigation means observing carefully and making notes. Some investigations require collecting numerical data and taking measurements, and a good scientist measures very carefully. When you know how to measure accurately, you can be confident about the results of your experiment. When you measure with a ruler, a thermometer, or a balance, you are limited by the precision of the instruments. But you must use them properly and read scales carefully. That's what we describe as accuracy. The basic rules are fairly simple, and they make sense. For instance, when you're measuring a liquid, you read the level at the center, not the sides. Water in a graduated cylinder has a concave meniscus, so you read volume at the bottom. This level represents the majority of the substance, introducing less error of measurement. For better accuracy, the meniscus should be at eye level. Even when you're measuring with a ruler, you need to take care. In case the ruler is slightly worn, start one major unit in from the end, in this case 1 centimeter, and deduct 1 unit from your measurement. Here's another useful skill.
Measuring mass with this.
Triple beam balances come in slightly different models, but they all work in a similar way. Start by making sure your balance is level.
So the indicator should be at 0, but it isn't, so we'll have to adjust the balancing net. There.
Now I'll place this beaker of water on the measuring pan.
And the indicator goes straight up.
So what's the first step in measuring the mass?
Well, we have to move the heaviest weight first. But that's too much, so I'll move it back 1 notch. And the arm is still above 0.
So what now?
Well, now we move the weight on the next beam.
Indicator's still above 0, though.
Right, so now we move the last weight. And since it's a slider, I'll move it with a pencil. There.
Right. The indicator is level. The mass on the pan balances the mass on the arms.
Right, so the mass of this beaker full of water is 161.9 grams.
Good. Lab measurements should be recorded. Table is a convenient way to organize your data. Choose an appropriate title, like this one.
20.6.
Dana and Brendan are using a table to record their observations of a moving bucket belt in a grain elevator. They've labeled the columns, including units. In this case, distance in centimeters is the manipulated or independent variable. It goes in the first column. Time, measured in seconds, is the responding or dependent variable. Recording data on a table should make it easier for you to interpret and analyze the results of your experiment. Any measuring instrument has limited precision. Stopwatches often display time to the nearest 1/100th of a second. That's precise, but it's still limited. With lab measurements, it can't be 100% accurate. There's always a small amount of error.
Using a school thermometer like this one, we usually record temperatures to the nearest half degree,
We round up if the measurement is half a unit or more.
and down if it's less than half a unit.
To indicate the precision of a measurement, we use significant digits. These are all the numbers that can be read from an instrument, like a ruler, a thermometer, or a balance, and one estimated number. The more significant digits, the more precise the measurement. Take a look at this measurement. How many significant digits does it have?
5.
And what about this one?
Well, just 2, since leading zeros aren't significant.
That's right. Leading zeros are just placeholders. We could express this measurement using scientific notation.
So what about trailing zeros after the decimal?
Like this. Well, trailing zeros are significant. They indicate more precision in the measurement.
So 9.600 meters has 4 significant digits.
Good. If you're adding or subtracting measurements, the answer is only as precise as the least precise measurement.
This adds up to 22.664 meters.
But 5.23 meters is the least precise measurement, so the answer can only be expressed to the nearest 100th of a meter.
Then we have to round off. Since 5.23 has only 2 decimal places, the answer has to be rounded off to the nearest hundredth of a meter, which is 22.66 meters.
Now, when you're multiplying or dividing, the answer can only have as many significant digits as the least precise value. Here we have a product of 14.314 centimeters squared. Can we leave it like that?
No, because the least precise measurement is 3.4 centimeters, and that's only 2 significant digits, so we have to round. So that's 14 centimeters squared.
Rules about measuring and recording measurements are all part of a scientific investigation. Following these rules helps you to be clear about how much you know,
And be honest with your results.
even when they don't match your predictions. Let's get a close-up on this. A little closer. Closer. There, that's got it. What you're looking at is a single plant cell. There's nothing like a microscope for bringing the invisible world into sharp focus. Most students begin by learning to use one of these. But before you focus the microscope, you need something to look at. Here's how to prepare a wet mount slide.
Here's a glass slide, a cover slip, a dissecting needle, and an eyedropper with some water. Now you can prepare a wet mount slide.
First, cut a small wedge potato with a scalpel.
Then smear some potato cells from the wedge onto the center of the slide.
Add a drop of water.
Attach the cover slip to the water and lower it onto the slide with the dissecting needle.
Okay.
What do you see?
Just a smear. I don't see anything distinctly.
Oh, the cells are there all right. They just need highlighting. You have to add a stain. A wood stain brings out the grain in this cabinet, and this dilute iodine will highlight the cells of the potato.
So instead of water, I'll add a drop of iodine. I see something.
So the grain starch in potato cells are highlighted by iodine. Some stains are used for plant cells, but others work better with animal cells, such as this nerve cell.
The nucleus really stands out.
Finding a specimen under the microscope and getting that image into sharp focus takes practice and a lot of patience. Once you have a slide prepared, place it on the stage and use the stage clips to hold it in place. Start with the lowest power lens. Rotate it into position, then raise the stage so the slide is as close as possible to the lens without touching. You'll have to watch from the side to make sure it doesn't touch. Use the coarse focus to lower the stage until your tissue comes into view. Then use the fine focus to sharpen the image. There, now you can see your wet mount. To get a closer look, rotate the lens to the next higher power. Again, you have to watch from the side so the lens doesn't touch the slide. Now use the fine focus to sharpen the image. Same slide, closer view. To get the closest look possible, repeat this using the highest power lens. Use the fine focus to sharpen the image. And there we have it.
This circle of light is field of view. It's what you see through the microscope's lenses. If you know its diameter, you can measure everything inside it. Why don't you give it a try? Start with the lowest power of magnification. The compound light microscope magnifies an image through two lenses, the objective lens just above the specimen and the ocular lens in the eyepiece. Each lens has its own magnification. Calculate the total magnification of a specimen, multiply the two values.
So at the lowest power, 40 times magnification, the field of view is approximately 4 millimeters.
Greater magnification means you're looking more closely at the subject. So as the magnification increases, the diameter of the field of view decreases.
Today's scientists have amazingly powerful microscopes, but we still use the trusty compound light microscope. It's simple, dependable, and gives us a window into worlds that can't be seen with the naked eye.
You can't always record your scientific observations on a table or graph, or even find the words to describe them.
Well, it's kind of bean-shaped with a sort of blob in the middle.
Sometimes you need to draw a picture. And when you do, there's a standard format to follow. Use a pencil on unlined white paper and choose one portion of the image from your field of view to draw. Make sure you use at least half the page. If there are several cells, you only need to draw one. And try to make sure that you keep the objects in proper proportion to one another. Using a ruler, draw horizontal lines from the drawing and label the parts of the structure. Add a title, and on the bottom right, place your name, along with the magnification and scale. If your field of view is 0.4 millimeters and the paramecium takes up about half that space, the paramecium is 0.2 millimeters long. With this information, you can calculate the scale of the drawing. The drawing gives a clear picture of what you saw through the microscope. Besides drawings, there are other visual ways to communicate information. Tables and graphs, for instance.
15 minutes and the temperature is 71.0 degrees Celsius.
A graph makes it easy to see overall patterns and trends, so it is often the best method to communicate numerical data.
Multiplying length times width.
Graphs work well for organizing all kinds of data. No matter what the subject matter, every graph follows certain rules. Let's look at an example.
On this graph, we're going to plot temperature and time, with temperature being the responding variable in degrees Celsius and time being the manipulated variable in minutes. And the temperature is minus 11.5 degrees Celsius.
Tanya and Brendan are plotting a graph to show how long they have to add heat before ice changes to water and water changes to vapor.
17.5 degrees Celsius, 19 minutes, and the temperature is 98.0 degrees Celsius. Now it's starting to change to a gas.
Another phase change.
Well, if your graph looks like this, or like this, you need to change your scale. All your data should fit nicely on the page, and it will if you choose a scale that's appropriate for your data. Here's a better example. See how the data fits comfortably into the graph space. So get the scale correct, and remember to label your axes and give your graph a descriptive title. With the data points entered, all that's left is to draw a best fit line, a smooth line that comes as close as possible to most of the points on the graph. Now remember that error we get whenever we measure something? Well, it shows up on our graph when all the data points don't fit on a line. Points that are right on a line should be evenly distributed, half below the line and half above. In some cases, you can analyze a graph and calculate a new quantity.
So every 15 seconds, we've got 15 times 1.1 kilojoules, which is 16.5 kilojoules.
And for every 15 seconds, it's the same for 3 minutes.
So at 30 seconds, we get...
Here Lorene and John are making an energy time graph to plot the energy used by a microwave oven.
5 kilojoules.
Time is the independent or manipulated variable.
6 kilojoules.
Energy is the dependent or responding variable.
5 kilojoules.
And your best fit line looks like this. Now, how do you calculate the slope of this graph?
Simple. Rise over run.
In this case, 140 kilojoules minus 10 kilojoules over 127 seconds minus 10 seconds.
Which is 1.11
And the units?
kilojoules per second. Hey, kilojoule per second is 1 kilowatt.
Cool. The slope of the graph tells you the power of the appliance, 1.1 kilowatts.
Slope of a line graph is often a meaningful quantity. In this case, Lorene and John were able to do a rise over run calculation and arrive at a new quantity, power. Another common way of analyzing a graph is to calculate the area under the best fit line. For instance, we can use a force versus distance graph to help us find out how much work is done.
This graph represents the energy change required to change the position of the sailboat. The y-axis represents force, and the x-axis, distance traveled. Suppose we have a constant breeze that provides 500 newtons of force to the sails. If the skipper keeps the boat on a constant straight course after, let's say, 20 meters, the graph looks like this. So how much work was done on the sailboat?
Well, work equals force times distance. In this case, 500 newtons times 20 meters, or 10,000 newton meters.
But check out the graph.
Okay, if we multiply force times distance, that's the same as multiplying the amount of x by the amount of y.
Good. Now if we think of this as a rectangle, multiplying the x value by the y value is the same as multiplying length times width. And length times width is area.
So the area under the curve would be 500 newtons times 20 meters. And that gives us 10,000 newton meters.
In other words, if the x-axis represents distance and the y-axis represents force, then the area under the curve equals the work done.
So you see, graphs display data from scientific investigations and make it simpler to analyze that data.
And the temperature is...
Remember when Brendan and Tanya added energy to ice until it turned to liquid and then vapor?
There was a period during melting where the temperature stayed the same at 0 degrees Celsius. And then it rises as the water heats.
And stays the same as the water boils.
We can see from their graph that the temperature remained constant at certain points. This was during a phase change, when the ice changed to liquid, and then when the liquid changed to vapor. All kinds of graphs are used in scientific investigations, like pie charts and a variety of bar graphs, including climate graphs. Choose whatever graph works best to communicate your data.
We spread the leaf right side up in a petri dish. and then place it on a piece of whiteboard.
We flood the leaf with an iodine solution and observe for several minutes.
Your scientific investigation may end with an evaluation. This often involves both an evaluation of results and process. These are some of the questions you might ask during your evaluation. Was your prediction verified or not? Was the experimental procedure adequate to answer the problem? Was the procedure appropriate for your level of skills and the equipment you have?
We see that the part of the leaf exposed to light contains starch. The part of the leaf shielded from the light doesn't.
So our prediction is right. Light is required for photosynthesis.
Yo, let's rap.
The practice of science requires specific skills. You need to know how to measure accurately and how to use basic equipment. You have to record and organize your findings clearly and honestly. Write up an experiment in a clear and concise manner so someone else can understand and repeat it. Science builds on previous knowledge obtained through skillfully conducted and documented investigations. You might say it's simply science.